Hi, my name is Kratuain binti Syamsul Bukhari.
Hi, my name is Nurin Shahira binti Zulfitri.
Hi, my name is Syamil Farah Amani binti Samar Zaman.
What is application of differentiation? Numerous real-world problem types can be resolved with the use of differentiation and integration. To find the maximum and minimum values of specific functions, such as cost, strength, the quantity of material required to create a structure, profit, loss, etc., we apply the derivative. Many science and engineering problems involve derivatives, particularly those that involve modeling the behavior of moving objects.
Why do we use differentiation? Applying differentiation is crucial because it gives us effective tools to comprehend and examine how functions behave and relate to one another in different situations. Differentiation allows us to precisely quantify how a function changes with respect to its independent variable. This is essential in understanding the rates of change in a variety of natural processes, including motion, development, and decay is crucial. We can determine the maximum or lowest values of function by locating critical points or places where the derivative equals 0. And by using the first or second derivative test, this is quite helpful in many domains when it comes to process, design, and decision optimization. Differentiation is used in physics and engineering to describe and analyze complicated systems, including electrical circuit, motion, heat, transport, and fluid dynamics. It offers perceptions into forces, acceleration, velocity, and other physical parameters. In economics, differentiation is often used to examine marginal concepts, which is marginal income, marginal cost, and etc., which are essentials for determining production, pricing, and resource allocation decisions. It assists in figuring out the best plans of action for increasing revenue or cutting expenses. Differentiation aids in process optimization, consistency, and efficiency assurance, and variation analysis in manufacturing and quality control. In conclusion, differentiation is a crucial technique in many fields, including applied science, engineering, and pure mathematics. It provides a systematic way to analyze how quantities change and interact in real-world situations. It has several important applications that are essential to comprehending and improving our planning.
Now, let's look at the examples of applications. Numerous domains, including physics, engineering, biology, economics, and more, have applications with related rates. In situations when various quantities are interdependent in the actual world, it is used to analyze and forecast how these quantities shift. According to theory, the reason link rates are so significant is that they have so many real-world applications. For instance, a gas tank company might want to know the rate to fill up a tank. Second, environmentalists might want to know the rate of a marshland floods. Let's take a look at another field. First, biology field. The situation is a population of animals is growing or declining. With related rates, we can determine how the growth rate of the population changes with respect to various factors, such as birth rate, death rate, or immigration. Second, engineering field. The situation is some fluid is flowing through a pipe or a channel. Related rates can help us to find how the flow rate changes with respect to the diameter of the pipe or the pressure applied at different points along the flow. Third, physics field. The situation is a ball is dropped from a height. The height of the ball decreases over time due to gravity. With related rates, we can calculate how the velocity of the ball changes with respect to time as it falls. Lastly, economics field. The situation is the changes price of a commodity in response to supply and demand. Related rates helps us analyze how the price changes with respect to changes in supply or demand using derivatives to understand the rate of change.
Problem statement. The diagram shows a spherical container with a radius of 14 cm. Water is poured into the container such that the depth hcm from the base of the container increases at the rate of 0.4 cm per second. A. Show that the surface area is cm square of the water in the container is given by A equals to pi in bracket 28h minus h square. B. Find the rate of change of the surface area of the water in the container when h equals to 4 cm. I will be explaining the answer for part A. It's given that the radius from the center of the spherical container is 14 cm and the depth is h cm. The length between the height and the radius is h minus r. So, to determine surface area, we have to calculate the radius of the surface area by using Pythagoras theorem. When r is equals to 14, r square is equals to r square minus in bracket square h minus r. R is equals to square root r square minus in bracket square h minus r equals to square root 14 square minus in bracket square h minus 14 equals to square root 196 minus in bracket h square minus 28h plus 196 equals to square root 196 minus h square plus 28h minus 196 equals to square root 28h minus h square. The surface area is A equals to pi r square. So, we substitute the r that we have calculated in the equation, which equals to pi in bracket square 28h minus h square, and cancel the square and the square root. The final answer is equals to pi in bracket 28h minus h square.
Now, let's move to the next question. Find the rate of change of the surface area of the water when the height of the container is 4 cm. The informations given were dh over dt equals to 0.4 cm per second and height equals to 4 cm. Now, let's find the differentiation of area. First, we use the area formula from the previous questions, which is A equals to pi times 28h minus h square. We expand the equation and it will become 28 pi h minus pi h square. After that, we differentiate area with respect to height. It will become d over dh times 28 pi h minus pi h square. We expand the equation and it will become d over dh 28 pi h minus d over dh pi h square. We differentiate the equation and it will become 28 pi minus 2 pi h. After that, we apply the chain rule formula, which is dA over dt equals to dA over dh times dh over dt. We substitute the dA over dh with 28 pi minus 2 pi h and dh over dt with 0.4. We expand the formula and we will get 11.2 pi minus 0.8 pi h. After that, we substitute the equation with 4 cm. dA over dt equals to 11.2 pi minus 0.8 pi h. Substitute the h with 4 cm, it will become 11.2 pi minus 0.8 pi times 4. We expand the equation and we will get 11.2 pi minus 3.2 pi. And the final answer is 8 pi centimeter square per second.
From the question that you have solved, we first understand that the surface area of the water forms a spherical cap. Using geometric principles, we derive the surface area formula for the water in the spherical container as A equals to pi times 28h minus h squared. Then, we differentiate A with respect to h and apply the chain rule to find the rate of change of the surface area. The final answer tells us that when the depth of the water is 4 cm, the surface area of the water is increasing at a rate of 8 pi cm squared per second. This means that as the water level rises, the surface area exposed to the water is changing at a specific rate, which can be quantified through differentiation.
Thus, in general, calculus-related rates problems offer an organized method of comprehending the relationship between changes in one variable and changes in another. These problems strengthen the relationship between theoretical calculus concepts and practical applications by utilizing implicit differentiation and the chain rule, two essential problem-solving techniques. By means of meticulous examination and precise formulation of equations, learners get a more profound comprehension of rates of change across diverse scenarios, ranging from geometric shapes to physical phenomena. Learning related rates can improve students' mathematical skills and equips us to handle challenging situations where knowledge of dynamic relationship is crucial.